Hey class, I've talked to a couple of you about this problem number 4 from the workshop. It's a pretty tricky one, so I thought I'd go ahead and make the first video of the semester for you guys about this. So as you can see in the situation, what we have is we have a car and a train. Alright, we're told that the car has a length equal to 101 meters, so maybe I'll label that here. It's 101 meters long. Okay. And we're told that it starts from rest. So if you see here in this picture, I've drawn pictures at time 1, time 2, and time 3. So I'm going to label what I got going on in each of those situations, because we're told in the process of reading the question that there's a time 1, when the train first starts going, that the car is lined up with the back of the train. There's a time 2 when the car has caught up to the front of the train, and then a time 3 where it's returned to the back of the train once again. Alright, so let's look at what we got going on here. So the velocity of the train when it starts in situation 1 we know is 0 meters per second. Alright, the velocity of the car in situation 1 is just the velocity of the car, right? We're told it's a constant speed, so it's not going to change. And we're going to define this initial time that we start at t1 as being equal to 0 seconds, right? We're going to just call our initial situation 0 seconds, alright? Now, we're also going to define the starting location of the back of the train and the back of the car in this case as being x equals 0, okay? Sounds good. Now, let's look at position 2. So now, in position 2, we now have a new time, alright? So we have time 2. We are told that 15.5 seconds have transpired. We can observe that the train has covered some distance. I'm going to go ahead and call the distance d here. And we can observe that the car has gone the distance d plus the distance l, which is the length of the train. Okay, so it's covered a larger distance, and it's still moving with its same velocity because it's moving at a constant velocity, and our train has some new velocity that we don't know because it's undergoing this acceleration. And so we're asked to find what the acceleration of the train is, which is going to be the same in each situation. And then lastly, in position 3, we can observe, well, I'm going to add a subscript up here, d1, because we're going to have a new distance in situation 3. We can now observe that the train has covered some distance, I'm going to call d2, and the car has also covered this distance, d2, as well, and it still has its same velocity because it doesn't change. Let me clean that up a little bit. The velocity of the car in position 3 is still the same velocity of the car. My equal sign doesn't want to look nice, so. And the velocity of the train is yet a new velocity since it's been accelerating that we still do not know. So when we first look at this, it looks crazy, right? We don't know the velocity of the car. That's something we're asked to find. We don't know the acceleration of the train. We don't know distance 1. We don't know distance 2. We don't know the velocity of the train at any different points in time. We might be able to find it using the times given, but we don't know it straight away. Speaking of the times given, we never wrote this one. T3 was given to us in the problem statement, 32 seconds. Alright, so we got all kinds of things going on here, and so what you're going to end up having to do in this problem is use multiple different equations and solving them together. So let's see how we might be able to do that. First, I will zoom out for us a little bit and scroll down, really mostly scroll down. And what we're going to do now is we're going to look at the car and the train at various different time. So what we're going to do is we're going to look at what we've drawn here. So the transition of the two vehicles from position 1 to position 2, and also from position 1 to position 3. So we'll look at both the train and the car. And in doing so, we're going to be looking at one primary equation of motion. And you can do it a couple different ways. Some of you might have used other equations of motion, and that's fine. But we're going to primarily be using our second equation of motion, which tells us x final equals x initial plus v initial times time plus 1/2 acceleration times time squared. Alright, so looking at starting with position 1 to 2, and we'll start with the train, which I'll write in red. We know that its final position, the distance it travels from position 1 to position 2 in time, is the distance d1, and that's going to be equal to our initial distance, which is 0, plus our initial velocity times time, which is also 0, which equals 1/2 the acceleration of the train multiplied by the time, which we have called t1 squared. So d1 equals 1/2 the acceleration of the time multiplied by t1 squared. Next, we can look at the car. Uh-oh, I hear a train coming through. That's my wife adding some entertainment and background music for us, which is awesome. That's the train sound that she made. Anyway, so the blue is for the car, and the car now, its final position, as we can see, is d1 plus L, and that's equal to its initial position, which is 0. We can see that here. Its initial velocity, which is just the velocity of the car, multiplied by the time t1, plus the acceleration of the car. Oh, I never mentioned that, did I? If we look up here, what do we know about the acceleration of the car? Well, for the entire time, we can observe the acceleration of the car is 0 because it's moving at a constant speed. Bonus, that's easy enough. So one thing I just noticed though is that our time 1 is actually when we started at 0. Its time 2 is the location after which the car has gone a distance d1 plus L and the train's gone d1. So I'm actually just going to make a quick change here that this should actually read t2, and this one here should also be t2, not t1. Sorry about that. Alright, so if we look at our equations here, what we can see is for the train, if we solve our equation here, for the car, we can solve it for d1. So d1 subtracting L from both sides is going to be equal to the velocity of the car times t2 minus the distance L. And if we notice now, what we have here is we have d1 here, and we have d1 here, and we know that d1 equals d1, and so since d1 equals d1, we can go ahead and solve, or set those two parts equal to one another. So let's go ahead and do that. I'm going to just scroll up here to give myself a little more room. Alright, so if we set d1 equal to d1, then what we should come up with is an equation that looks something like this. 1/2 the acceleration of the train multiplied by t2 squared is equal to the velocity of the car times t2 minus L. Alright, so we got an equation here, and if we look at it closely, what we see is we still have two things we don't know: the acceleration of the train, which we're trying to find, and the velocity of the car. Okay, well that's good, but bummer that we can't solve yet. Now the question is, can we get another equation with those same two unknowns? Two equations, two unknowns we can actually solve, right? So now if we look at what happens from the beginning all the way up until time number 3, which is point 1 to point 3, let's see what we can have. So if we notice, in both cases for the train and the car, they've covered a distance equal to d2. So we can say for the train, d2, going with our same equation, its initial position and velocity are both 0, so it's just 1/2 the acceleration of the train multiplied by t3, the time at the end, squared. And for the car, switching to blue here, For the car, what we see is that d2 is equal to just the velocity of the car multiplied by t3. So now, once again, just like last time, we know that d2 is equal to d2 since they're the identical things, and we can then set them equal to one another, so we get the equation 1/2 the acceleration of the train times t3 squared equals the velocity of the car multiplied by t3. So, as you can see here, we now have two equations with the same two unknowns. We know the times and we know L, so what you can do is you can actually do substitution, combine these two equations, and solve for the same two unknowns. So there's still a little bit of tricky stuff you can need to do, but as you can see, T3, one of those would cancel out, so you already have VC equals some value which you can plug in for the velocity of the car in this equation in order to solve. So give that a shot and let me know if you have any additional questions.